Hi everyone, my name is Askar and I'm a postdoctoral researcher at Lund Observatory where I work with Melvin Davies and Ross Church. In this talk, I'll be talking about formation of intermediate mass black holes in dense stellar clusters. Intermediate mass black holes are black holes in the mass range of about 100 to 100,000 solar masses. They're the missing link between stellar mass black holes and supermassive black holes. Supermassive black holes are in excess of about 1,000,000 solar masses and found at the center of galaxies. And it's possible that they grew from lower mass black holes, which went through the intermediate mass black hole regimes. So essentially, there are three main formation mechanisms for supermassive black hole seeds. They could have formed from the gravitational runaway mergers of stars or black holes, resulting in the formation of an IMBH. They could have formed from remnants of population 3 stars in the early universe, which then grew substantially to become the supermassive black holes that we see at the center of galaxies. Or it's possible that in the early universe, a large amount of gas directly collapsed to form heavy black hole seeds of about 10 to the 5 to 10 to the 6 solar masses, which then became supermassive black holes. These different formation mechanisms for supermassive black hole seeds have a consequence on the present-day supermassive black hole mass function, the occupation of supermassive black holes in different galaxies, and also on how the supermassive black hole mass correlates with the mass of the host galaxies. So far, there's no concrete evidence for the existence of IMBH, particularly in the range of about 100 to 10,000 solar masses. However, there are several promising candidates. If you would like to read more about intermediate mass black holes, please check out this review from Green, Strader, and Hope. So in my talk today, I'll discuss the possibility of forming black holes of about 100 to 10,000 solar masses in dense star clusters with central densities of about 100,000 solar mass per cubic parsec or larger. What can happen in these dense star clusters is that early on in their evolution, the massive stars can segregate to the cluster center due to dynamical friction. And before they evolve, they can undergo runaway collisions with each other, resulting in the formation of a supermassive star, which could potentially evolve into an intermediate mass black hole, or could also merge with a stellar mass black hole, resulting in the formation of an intermediate mass black hole. The second possibility is your massive stars evolve into black holes, which then segregate to the cluster center and undergo runaway mergers, resulting in the formation of an IMBH. And the third possibility is that the stellar mass black hole increases its mass gradually through mergers during dynamical interactions or by forming binaries with regular stars and then having episodes of mass transfer. So the IMBH formation in clusters can be divided up into two regimes. You can either have fast formation, in which a 100 solar mass black hole seed can form within few to 100 mega years of the cluster evolution. This typically requires high initial central densities in excess of 1,000,000 solar mass per cubic parsec. Or you could have a gradual buildup of your stellar mass black holes at a later time when the cluster is collapsing and the stellar mass black hole can undergo interactions in which it merges with other stars or forms binary systems in which mass transfer can occur. This does not require very high central densities. The final black hole mass also depends on these two different regimes for the formation of the seed. Here we show the mass of the intermediate mass black hole at 12 gigayears versus its formation time of its seed. And typically, if you form the seed within a few tens of mega years of the cluster evolution, then the 12 gigayear black hole mass is about 10 to the 4 solar masses or larger. But in the slow formation scenario, if you form the black hole seed after a gigayear, then typically the final black hole mass at 12 gigayears is between a few hundred to 1,000 solar masses. So the first thing I want to discuss is the impact of IMBH formation on cluster initial conditions, and particularly the natal kick prescriptions and the initial cluster mass that you have. So in these simulated star cluster models, we consider two cases where we gave black holes kicks as high as neutron stars, or we scaled down their kicks due to fallback prescriptions, or assuming that the final black hole kicks depends on the final black hole mass of the black hole mass. So we find that in a cluster where we have about 2,000 black hole progenitors, we can retain about 50% of them if the black hole kicks are lower. But if you give them the same kicks as neutron stars, this retention fraction can be as low as 1% of 1%. And the main point here is that the probability to form an IMBH increases with cluster mass and density. And for massive star clusters, the kick prescription for black hole natal kicks is not so important, because in these cases, especially when densities are high, the main buildup is through main mergers of stars. But for lower mass clusters, you need to retain a few black holes before they can grow into an intermediate mass black holes. And in that case, you require low black hole natal kicks. So now I'll discuss about how the dynamical interactions lead to the IMBH seed formation. So essentially the two regimes can be seen here. So first one is the runaway mergers between main sequence stars and dense clusters. So what I have plotted here is about results from about 400 star cluster simulations in which we form an IMBH. And here what you see is the maximum main sequence mass that we obtain in the system, and then the initial black hole, massive black hole mass that we get. And what we see here in these models up here is that we have built up a significant main sequence mass, which then merges with a stellar mass black hole, resulting in the formation of a massive black hole. And the colors in this plot represent the initial cluster density. So when the cluster densities are high, in excess of 10 to the 6 solar mass per cubic parsec, then this regime is, then we see this, this branch of IMBH seed formation. However, there's also, for lower clusters, the initial black hole mass, which then becomes the seed of intermediate mass black holes, is lower. And this is the case in which you have gradual growth of the stellar mass black hole in low density, in initially lower density clusters. The main caveat in these simulations is that when a massive main sequence star merges with a stellar mass black hole, then all of the mass of the black hole is accreted by, then all of the mass of the star is accreted by the black hole. And this is one of the caveats, but we also consider cases where only 25% of the star mass is accreted by the black hole, and still we can produce massive black hole. So what we find is that massive seed black holes are preferentially formed in denser clusters via gravitational runaway. And lower density clusters form lower mass seed black holes, and then the final black hole mass is also lower. And this is the gradual buildup case. Once you form the IMBH seed, there are three main processes which lead to its growth. One is tidal disruption and capture events. So this is some preliminary work that we are looking into. What we essentially find is that in each cluster, you have about 0.1 such events per every mega year. And this contributes to the growth of the IMBH. Initially, this is a much higher rate, but as with time, this rate goes down as the IMBH becomes more massive. And also, we see that in the lower mass cases, the mass transfer in binary systems can also contribute to the growth of the intermediate mass black hole. So it forms binary with a regular star, then it takes a mass from the star or eventually merges with the star, then forms a binary with another star. And all these processes are gradually contributing towards its growth. One other thing to consider when you're merging, when you're growing the seed black holes is what happens when it merges with another stellar mass, with a stellar mass black hole. Because when two black holes merge, you have the gravitational waves emission from the merger carries away linear momentum, and the final black hole can get a recoil kick. And this recoil kick depends on the mass ratio of the merging black holes and also on the spin magnitude and orientation of the black holes. So essentially, to keep the seed black hole in the cluster when it merges with another black hole, you need the mass ratio to be very low. So here we show what the typical kick velocities can be for different mass ratios of merging black holes. And in order to retain the merged black hole in the cluster, where typical escape velocities are of the order 50 kilometers per second, you really need the mass ratio to be lower than 0.1. So we looked into this in a paper by Murawski and collaborators, where we checked in how many cases we could retain the black hole seed from these 400 simulations. And we find that in about 20 to 30%, the initial mass of the black hole seed is large enough that when it merges with the lower mass black holes, the recoil kick is low enough that it can be kept in the cluster. So intermediate mass black holes have quite a few consequences for future gravitational wave detections. What can occur is that if you can form these intermediate mass black holes in dense star clusters, then some of these star clusters could infall into the galactic nucleus due to dynamical friction. And this infall of the clusters bringing along IMBH can then populate the galactic center with intermediate mass black holes. And I would recommend checking out the talk by Melvin Davies on how this could result in the formation of a supermassive black hole or a supermassive black hole seed. But what's also possible is that these IMBHs in stellar clusters will be delivered to the galactic center, where they could then merge with supermassive black holes, resulting in intermediate mass ratio in spirals, which could be interesting from the point of view of LISA. Then there's also the possibility of having multiple multiple intermediate mass black holes delivered to the galactic center, where they could potentially form binaries and merge with each other. And such mergers towards in the final stages could be observed in the LISA band in the relatively local universe. So, and then there's also the possibilities of intermediate mass black holes merging with stellar mass black holes in the clusters, which could also generate unresolved gravitational wave background signals. So in conclusion, dynamical interactions in dense star clusters can lead to the formation of intermediate mass black holes of about 100 to 10,000 solar masses. What we find through numerical simulations is that if the clustered central densities are larger than about 1 million solar masses per cubic parsec, then we can form a IMBH through runaway mergers. In lower density clusters, we can also see the buildup of a stellar mass black hole through mergers during dynamical interactions, but this process is more stochastic and it results in the formation of lower mass intermediate mass black holes. And then the important point is that the intermediate mass black hole can also grow in the stellar clusters through mainly through tidal disruption and capture events. And then stellar clusters containing intermediate mass black holes could merge with the galactic nuclei, where they could then potentially merge with each other or merge with the supermassive black hole. So just to end, here's another plot from the review by Greenstader and Ho, showing the nuclear star cluster mass versus the black hole star mass that they harbor. And these are some upper limits for different nuclear star clusters and nuclei. And these are upper limits from globular clusters. So upper limits based on observations suggest that at least galactic globular clusters do not have a black hole more massive than 1,000 solar masses. So it's still possible that they contain lower mass IMBHs. And it's also possible that the clusters that did contain intermediate mass black holes have already merged with the galactic nuclei. So this was my talk and a general overview of the ways an IMBH could form in stellar clusters. Thank you for your attention and for listening to my talk. If you have any questions, please feel free to contact me. Thank you.